How cameras and mobile phones work, and how lenses detect color. Introduction. The camera is one of humanity's most remarkable inventions, a small device capable of capturing a moment in time and preserving it forever. Today, almost everyone owns a camera, in a smartphone, laptop, tablet, or even a smartwatch. But have you ever wondered how this device actually works? How does light enter the lens, fall on the sensor, and finally turn into a sharp, colorful image? And how do lenses distinguish between different colors? To answer these questions, we must start from the beginning with light, the human eye, and the laws of physics. In essence, cameras are nothing more than an imitation of the human eye. The lens functions like the eye's cornea. The aperture acts like the pupil, and the sensor works like the retina. In this article, we will explain all these stages from the perspectives of physics, optics, and electronics in a simple yet scientific manner. 1. Light and its role in photography. Everything begins with light. Without light, there is no image. Light is a collection of electromagnetic waves emitted by sources such as the sun or lamps. These waves have different wavelengths, which correspond to different colors. For example, red light has a longer wavelength, while blue light has a shorter one. When light hits an object, some of it is absorbed, and some is reflected. The color we see is the color of the reflected light. For instance, a red apple reflects more red light and absorbs the other colors. Cameras record these very reflections. 2. The lens, the eye of the camera. The lens is the most important part of any camera. It consists of several glass or plastic elements arranged in a specific way to bend, refract light, and focus it onto a specific point called the focus. If the focus is incorrect, the image appears blurry. 2.1. Focal length and field of view. Lenses are categorized based on their focal length. Lenses with short focal lengths, for example, 18 millimeters, have a wide field of view and are suitable for landscapes. Lenses with long focal lengths, for example, 200 millimeters, are used for distant photography and are called telephoto lenses. 2.2. Aperture and exposure. Inside the lens, there is a part called the aperture, which works like the eye's pupil opening and closing to control the amount of light entering. The aperture size is indicated by an f number. A smaller number, for example, f divided by 1.8, means a wider aperture and more light entering the camera. 2.3. Autofocus. Modern cameras, especially smartphones, use autofocus systems. The camera's sensor analyzes the scene multiple times to determine which part is sharpest. Then a small motor inside the lens adjusts the lens elements to achieve perfect focus. 3. The sensor, the electronic retina. In digital and mobile cameras, the sensor is the key component that converts light into digital data. There are two main types of sensors. 1. CCD charge-coupled device. 2. CMOS complementary metal oxide semiconductor. Each sensor is made up of millions of tiny pixels, each acting like a light-sensitive cell. When photons of light strike a pixel, a small electrical current is generated inside it. This current is converted into a digital value, ultimately forming a digital image. 3.1. CCD versus CMOS. In the past, professional cameras used CCD sensors because they produced higher quality, lower noise images, but they consumed more power. CMOS sensors, however, are faster, more energy efficient, and cheaper to produce. That's why nearly all smartphones today use CMOS sensors. 3.2. Resolution. The number of pixels on the sensor determines the resolution of the image. For example, a 12-megapixel sensor has 12 million pixels. More pixels mean more detail, but if the sensor is small, too many pixels can increase noise instead of improving quality. Number 4. How cameras detect color. Now we reach the main question. How do the lens and sensor understand color? The lens merely directs light color detection is the responsibility of color filters and image processing algorithms. 4.1. The Bayer color filter. Since each pixel measures only the intensity, brightness of light, a color filter must be placed in front of each pixel. The most common pattern is the Bayer filter, consisting of 50% green filters, 25% red filters, 25% blue filters. There are more green filters because the human eye is more sensitive to green light. 4.2. The demosaicing process. Because each pixel captures only one color, the camera must estimate the other two. This process is called demosaicing. The software averages and interpolates the colors of neighboring pixels to reconstruct the full color image. 4.3. White balance. White light varies under different conditions. Lamplight is yellowish, while sunlight is bluish-white. To make colors appear natural, the camera measures and adjusts the color temperature using white balance correction. 4.4. Dynamic range and HDR. The human eye can see both bright and dark areas at the same time, but sensors cannot. HDR, high dynamic range technology, takes several images at different exposures and combines them so that both bright skies and dark shadows are visible in the final photo. 5. Image processing in modern smartphones. Smartphones today are no longer just image capturing devices. They are image processing computers. When you press the shutter button, your phone usually captures multiple frames in quick succession and uses artificial intelligence to combine them for the best result. 5.1. Scene detection. Smartphone cameras can recognize what you're photographing: a face, landscape, meal, sky, or flower, and automatically adjust colors, contrast, and exposure accordingly. 5.2. AI-based color enhancement. Modern algorithms like deep fusion or AI color correction use machine learning on thousands of real-world images to reproduce skin tones, skies, and plants more naturally. In other words, the phone doesn't just capture the image, it interprets it. 5.3. Computational photography. For night shots, smartphones capture multiple frames, remove noise, and increase brightness. Sometimes multiple lenses, for example wide and telephoto, are combined to create one more detailed image. 6. Factors affecting color accuracy. Even the best sensors cannot reproduce colors accurately without proper lighting. Important factors include lens quality. The clearer and more distortion-free the glass, the more accurate the colors. Lighting. Natural sunlight is best. Artificial light often distorts color tones. Color calibration. Manufacturers use standardized color charts to match sensor colors with real-world hues. Image format. RAW files retain colors more accurately, but require processing. JPEG files compress and simplify color data. 7. The future of cameras and emerging technologies. In the near future, the concept of a physical lens may change dramatically. Researchers are developing computational lenses which use algorithms instead of glass optics. Other innovations include stacked sensors, which increase processing speed, adaptive pixel sizes, which change depending on lighting conditions, quantum-based color detection, which captures the full spectrum of light more accurately. In essence, the cameras of the future will not only see, they will understand. Conclusion. Modern cameras are a brilliant combination of physics, electronics, and artificial intelligence. From the moment light reflects off a scene until the image appears on the screen, dozens of physical and computational processes occur. 1. The lens focuses the light. 2. The aperture and shutter control the amount and duration of exposure. 3. The sensor converts photons into electrical signals. 4. Color filters separate the data into RGB channels. 5. The image processor, ISP, adjusts color, brightness, and sharpness. 6. Artificial intelligence analyzes the scene for optimal results. The result is an image captured in just fractions of a second, but backed by decades of science and technology. Cameras have become the second eyes of humanity, eyes that grow smarter, sharper, and more creative every day.